When we want to add new elements to the stack, we use the push operation. For example, if we push 9 to stack 578, the result is the stack 9578. But what if we want to insert 9 to the bottom of the stack? For example, if we insert 9 to the bottom of the stack 578, the result we want is the stack 5789. In order to insert 9 to the bottom, we must first pop all the elements. Then, we push 9 to the empty stack. Finally, we push all the popped elements back to the stack. Here's a demonstration. And here is a sequence of events expressed as a table. First, 5 is popped from the stack and pushed to the pop stack. Then 7 is popped from the stack and pushed into the pop stack. Finally, 8 is popped and pushed to the pop stack. Then we push 9, and then we start popping from the pop stack and pushing it back to the stack. So first 8 is pushed, then 7, then 5. Notice how the popping sequence was 578, but the pushing sequence was 875, or the reverse of the popping sequence. At Logic Walk, the process of adding to the bottom of the stack is called appending to the stack. This is analogous to appending to a list, which adds an element to the end of the list. For example, the result of appending 4 to the stack 1, 2, 3 is equal to the stack 1, 2, 3, 4. Let's take another look at this process. We started by popping all the elements. We kept the popped elements in a new stack since we need to push them back in later. This is equivalent to dumping the initial stack to an empty stack. Next, we push the new value to the now empty stack. Finally, we push the popped elements back into the stack. This last step also turns out to be a dump operation. More precisely, suppose we want to append V to stack S. First, we dump S to an empty stack. Then we dump the new stack to stack V. In other words, the result of appending V to stack S is equal to the result of dumping X to stack V, where X is the result of dumping S to an empty stack. Let's see some examples to better understand the right side of the equal sign. Suppose the stack is initially 1, 2, and we want to append 3. Then the right expression becomes the result of dumping X to stack 3, where X is the result of dumping stack 1, 2 to an empty stack. First, let's evaluate the child expression. The result of dumping stack 1, 2 to an empty stack is equal to the stack 2, 1. Using substitution, we claim that the result of dumping the child expression to stack 3 is equal to the result of dumping stack 2, 1 to stack 3. Next, we claim that the result of dumping stack 2, 1 to stack 3 is equal to the stack 1, 2, 3. Using the transitive property, we can conclude that the result of appending 3 to stack 1, 2 is equal to the stack 1, 2, 3. Here's another example. Suppose that we want to append some value V to an empty stack. The result of appending V to an empty stack is equal to the result of dumping X to stack V, where X is the result of dumping an empty stack to an empty stack. But the result of dumping an empty stack to an empty stack is just an empty stack. And the result of dumping an empty stack to stack V is just stack V. Unsurprisingly, appending a value to an empty stack is equivalent to pushing an element to an empty stack.